Right, is this thing on? Can everybody hear me at the back? I'm not one of the world's loudest speakers. This is a talk that has been growing and modified several times. I have a stiff timekeeping piece to do. The most recent few times I've done this, it's been over an hour, so we don't want to go there because I'm between you and getting some refreshments and so on. But if I go too fast, for God's sake, this is interactive. There are real presenters here, nothing virtual, and you should immediately say, hold it, go back, do that again. But we're going to talk about the future of microprocessors, by which, of course, I mean I'm going to talk about the future of microprocessors with copious examples from the past, because having examples from the future is actually quite hard. I have a wireless mouse thingy, which hopefully I'll be able to use. So the talk's structured around two very famous laws, but we're also going to delve into all sorts of other things. The talk is fairly technical. There are graphs. So the first law, which is kind of the obvious one, is, well, it's not a law. He made an observation that he looked at the rate at which the number of transistors on a piece of silicon was increasing over time and said, right, we can plot a straight line graph of that. When he originally proposed it, it was the number of transistors doubles every 18 months. Every 3 years, you got 4 times as many transistors onto the same piece of silicon, same area of silicon. It had a bumpy ride for a while, and they rewrote the law. The Silicon Valley napkin it was written on was torn up, and it was redrafted as every 2 years we get twice as many transistors. And the so-called law is now a self-fulfilling prophecy, because the law is taken as the driving force for the development of silicon processors, for making things. So the ITRS, the International Technology Roadmap for Semiconductors, who guide the development of future silicon processors at all the places that still make transistors, take the law and say, it has to be fulfilled. What do we do now to make that happen? What technology do we have to deploy? What weird materials do we have to get into? We can see that over the past 30 years, 40 years, it has actually held quite well. That is a remarkably straight graph in a world where not much is straight. We've used a lot of transistors to make things go faster. Because I got the graph from American sources, ARM isn't on here. The blue dots are Intel, the red dots are Motorola. Whatever happened to them? It gets very blue at the top right, as inevitably it must do. Log scale on the left, linear scale on the right. So that's how to convey the doubling as a graph. So remarkably, it has been possible to do this. What does it mean? We've, from this point on the graph, 8286, 8386, these things have executed the same instruction set going forwards. So they've used a lot of transistors to make increasingly complex versions of the same instruction set processor. Well, that's one way you can use a lot of transistors, but there are other ways. Another way to visualize the graph is to draw the same functionality. So on the wall behind me is a plot of the original 3-micron ARM1. In my right hand is a small piece of paper. On the small piece of paper is a black dot. The black dot contains a plot to the same scale of a modern-day Cortex-M0 Plus. And that's the rough modeling equivalent of the original ARM1. So pretty dramatic. It's 70,000 times scale change for the same functionality. Well, we designed this thing by hand and laid the transistors out perfectly, but that was done by a silicon compiler. So you could probably have done slightly better. So yeah, incredible change in what you can deploy. The small black dot obviously runs faster because the small transistors are better as well. Let's go back in time. What do you get for transistors? I design microprocessor instruction sets for a living and fun and profit. And what do you get for 4,000 transistors? Well, on the left is a die shot of the 6502. It's built out of silicon and metals. The colors are diffraction. Well, diffraction and refraction. So as we shine a light into a piece of silicon, we get refraction effects. Metal grids cause diffraction effects. So all the colors on these sorts of shot are entirely created by those processors. If you took a picture normally, it would just be a sort of copper-colored ingot of stuff. You have to go a long way. On the right-hand side is the circuit diagram of a 6502. And we've distorted the circuit diagram so the transistors are topologically in the same place as they are on the actual chip. Okay, so we won't do much more because as the number of transistors goes up, drawing circuit diagrams for things gets rather impractical. But you can see this big yellowy area at the bottom. That's the 6502's instruction decoder, and that corresponds to this part of the circuit diagram, which is the instruction decoder PLA as a schematic with the two PLA layers, black and white dots, meaning ones or noughts in the main PLA. Up at the top, we have the data path of the 6502, and in the middle, all the control logic. So, as I say, we won't be doing it by the circuit diagram as we go forward. We'll be doing it by a schematic diagram. The schematic diagram of the 6502 is on the right. It's a lot simpler than the circuit diagram. Basically, you get a set of blocks connected by buses. Pretty much all schematic diagrams of a microprocessor look like that, and camouflage practically every part of the intent of what one might mean. In this, we have things like accumulators, we have buses carrying things around the place, addressers going around, and so on. It's still probably a bit complicated. As we get more complicated microprocessors, we'll find that that diagram gets simpler. The more complicated the processor is, the less easy it is to explain just what is going on in there, and we draw simpler diagrams to compensate. The theme in the talk will concentrate on the words on the left. So what do we get for 4,000 transistors? We get something that has a fairly simple in-order microarchitecture. The 6502 was almost pipelined, but not quite. It could execute a 16-bit instruction which it read as two 8-bit quantities in the time it took to read it into itself. That was a good deal faster than some other processors of the time took. So an 8-bit operation, which is all it did. Add with carry immediate 9, that was a 16-bit instruction. It took 1 microsecond or 2 clock ticks. It read the add with carry in on the first. It read the 9 in on the second. And in the third, when it was reading the next opcode in, it actually did the add with carry 9. So it was just one level pipelined. It had a program counter, which was 16 bits, and 3 8-bit registers. And it was still 21 square millimeter in size because it was built on this gigantic 6-micron process. Now, I always qualify it by saying 6-micron smallest feature size, but in fact there's nothing in a 6-micron process that is drawn as small as 6 microns across. A transistor's substantially bigger than the thing that we call the smallest feature size. The name we give to a process, like we say 28 nanometer, everything in a 28 nanometer transistor is far larger than 28 nanometers. It's almost the smallest dimension you could possibly have claimed if you didn't matter that you were lying a bit. And the lies are large from many of these manufacturers. In the end, all we can actually do is count the number of transistors on a piece of silicon. So you didn't get something staggeringly complicated. 6502 has almost no registers. It keeps a lot of stuff in memory, 0 page for anybody who's ever programmed it. It takes substantial amounts of time to do even the simplest things. A whole microsecond to do that. You can only do 1 million of those a second. And obviously it takes a genius like David Braben or somebody to, with Ian Bell, to write Elite using a microprocessor as poor as this. But it was all we had at the time, and we were quite happy. When we came to design the ARM, we could use a lot more transistors. Now, even though we changed sort of technology from the 6502, which is actually a complex instruction set computer, the complexity isn't in the complexity of the instructions. When we differentiate between complex instruction set computers and reduced instruction set computers, what we're talking about is the complexity of the instruction decoding and how it's executed. That's what we mean. So 6502, remarkably simple instruction set. Surely that isn't a complex instruction set computer, but it is. And ARM, a substantially more complicated instruction set as it would appear, but it's a reduced instruction set computer because the complexity of decoding instructions is much, much simpler than it was before. And we can use 25,000 transistors now. Gordon Moore's wheel has turned. We can use some more. And this is what you get. Another die shot. Substantially prettier. I think you can see immediately that there's structure in this. This is because hand layout, when you're designing big structures, gives you interesting properties. If you remember the picture of the 6502, you could see some stuff in there. There were regular things, but the 6502 design is so messy that there's no metastructure. ARM's design is quite clean and clear, and thus the metastructure gives you some very obvious things. On the left is Steve Ferber's original pencil sketch of the data path of the ARM, now a historical document in its own right. So what do we get with these 25,000 transistors? Oops, I've gone the wrong way. Next slide, next slide. There. It's gone into some funny mode. We get a machine that's substantially faster, the transistors are faster, and we have enough transistors to pipeline the whole processor rather than just the instruction decoder as the 6502. So pipelining. Processors don't run at the clock speeds you think they do. So when we advertise a processor as running at 8 megahertz, it takes many more steps than one single 8 megahertz clock tick to execute an instruction in its entirety. So we need to do several fundamental things to do an instruction. On this processor, we needed to fetch it from memory, we needed to decode it, we needed to read the register file, execute the actual functionality required, and then write the result back to the register file. And we call the process of overlapping all those steps pipelining. So if we do a fetch while we do a decode and execute, while we do a write, if we put those things underneath each other again and again, then every cycle we can start the next fetch while the previous decode is going and the previous execute is going. And that's pipelining. And pipelining causes a lot of transistors to be used. More and more state is held in the processor because obviously it's thinking about things twice. We fetched the instruction, then we decoded the instruction and passed that decoded data on to another guy who did the execution while we fetched another one. So we've got state twice, and that pipeline state costs us lots of transistors. So on very simple processors built with low numbers of transistors, we simply can't afford to pipeline very much. As we've been given more and more transistors, we've been able to put more and more sophisticated pipeline architectures underneath things, many more stages. If we can cut things up more finely, then we can run the thing faster. So this is 3-stage pipelined. So it goes fetch, decode and execute, write. Those are its stages. If we went fetch, decode, register, execute, write, that's a 5-stage one, and we can run faster because each stage is now doing less work. And so the more highly pipelined you make your processor, the faster it goes. And the more transistors we burn and the more power we burn. So it's all about finding a balance. So with 25,000 transistors, we can make a 3-stage pipelined processor. So running at 8 megahertz with a 3-micron transistor, the 3-micron transistor was about twice as fast as the transistors they used to build the 6502. But the 6502 only ran at 2 megahertz. If we'd scaled just on the transistor's performance going from one to the other, we'd have only been running at 4 megahertz now. But we were also able to spend transistors to be pipelined. And that parallelism, that internal parallelism inside the machine, made it faster. Everybody else nodded off. So pipelining makes the processor run faster, but we burn transistors. We've also got enough transistors to make the data paths much, much wider. So our fundamental operation in an ARM compared with a 6502 can be much more interesting for programming purposes. We have a 32-bit operation. We can add register 1 to register 2 and put the result in register 0. And that can be done. You can start a new one of those every 8 megahertz clock tick. It doesn't take only one 8 megahertz clock tick. It takes 3 to actually do it. The latency is 3, but we can start a new one every clock tick. It's 37 square millimeters in size, so it's a bit larger. Shrinking from 6 to 3, getting 4 times as many transistors in the same area, isn't enough to burn 25,000 transistors in the same area that somebody was burning 4. So we are a bit bigger in this 3-micron process. The picture of an ARM, this is an ARM 2, ARM 2AS. Same blocks, same buses connected around the place. Block at the right-hand side saying instruction, decode, and control, where all the stuff is done. The buses grew to 32 bits wide, whereas they were 8 bits wide on the 6502. Addressers are 24 bits wide, where they were 16 bits wide before, and so on. So same sort of diagram, well, simpler diagram than the 6502s, but much more going on under the surface. The project that made ARM, we were concerned about being able to program things. It took David Braben and Ian Bell together to write Elite, and they had to slave over using the 6502. It was really hard. We wanted people to be able to write games as complex as Elite, but to do it much more easily, or even to use a high-level language instead of having to write it in machine code. So that was one of the rationales for going up in compute performance so much. When we made ARM, it was one of the most powerful microprocessors anybody had devised. Substantially more powerful than CISC. But that was a long time ago, and you may have noticed that there have been more transistors provided then. What does an instruction set designer do when she's given more transistors than that? So this is the FirePath processor. This is what happens when you're allowed to use 6 million transistors on the instruction set design. FirePath also is burning some transistors on a better pipelining implementation. This thing has an 8-stage pipeline, so it does burn some pipeline transistors. But substantially, with 8 million transistors, we can have a much more complex instruction set than you've seen. Most of the processors people in the room use have simple instruction sets with vastly complicated implementations. This is what happens if you are given a lot of transistors to use on making the most complex instruction set you'd like to. You can see that there's still some structure in here, but 6 million transistors, there's far too many to show. The pictures go a bit blurry. This is 125 nanometer, I think, 130 nanometer. So it's actually quite hard to take an optical picture of it. The obvious things, there are buses whizzing about the place. These big yellow striped radiator-looking things, they're the register files. It's got two of them. You can sort of see that the top and the bottom are the same. Part of this processor is built by replication, and then down the middle is all the control logic. But that's quite complicated, so we usually look at a much simpler picture of it. So FirePath is a long instruction word processor. It runs really quite fast. The 130 nanometer transistor process that it was built on gives quite fast transistors, and it's deeply pipelined. So 330 megahertz. It's designed to execute 4 64-bit operations per cycle. Pipelined, remember. You can start a new one of these every cycle, but they take multiple cycles to actually work. So an example of a FirePath instruction. This isn't a compound instruction or anything else. This is a single instruction that the processor executes in one gulp. So it says, add, I kept this to adds, but that could have been a multiply. FirePath is full of multipliers as well. So take a register pair R2, R3, a register pair R4, R5, add every separate subword of those registers and put the result back in R2, R0, while at the same time, in the same instruction, loading the register pair R6, R7 using the address you find in R8. And it can do that continually every cycle. So you can design instruction sets at a high level that take a lot of complexity, do a lot of work in one go. How am I doing? Whoa. It's quite small, 7 square millimeters. So even though I used 6 million transistors, the transistors have shrunk rather a lot.
Where did this fit in the history of things?
VLIW and LIW processors are a little bit rare in the histories of things. The history is written by people who sell lots, Intel.
Was this one ever actually made or sold?
Oh yes, FirePath is made and sold. If you have an ADSL line anywhere in the world, there's about a 90% chance that there's a FirePath at the other end of it. FirePath is also used in set-top boxes and inside TV chips, in femtocells, in power line modems, and lots of other things. We sell about 90 million FirePaths a year. Well, probably more, actually. That's a little bit out of date. About 130 million FirePaths a year. So yes, this is an active chip. I'm only allowed to talk about obsolete ones, however, which is why this is from 2003. So FirePath is quite interesting. It's SIMD throughout. So our block description of the machine, everything is single instruction, multiple data. So it has 64-bit data paths through it. Can afford lots of transistors on widths of things. And we can afford to do byte, half, word, and long versions of every instruction. So it's got a massive instruction set. And as I said earlier, it can do multiplies just as cheaply as anything else. So that could be a mul, or indeed that could even be mul B, in which case that single operation is doing 16-byte multiplies. And you can have one of those every new instruction. FirePaths are used for signal processing, so you end up doing an awful lot of that sort of thing, which is why it's worth spending the transistors. So what do you do after that? It's pretty difficult to complexify an instruction set beyond FirePath's level of instruction. So inevitably, if somebody gives you more transistors, you tend to say, I'll put down more microprocessors then. So this is a die with 2 microprocessors on. There's one, and one going the other way. It's typical of a die for any of the modern signal processing world in that it basically contains microprocessors and memory. All these regular single-colored blocks are large slabs of memory. So most of the interesting parts you take apart look pretty much like this. So we've burned some transistors and used up 2 fire paths worth of transistors, 6 million transistors ago. Handle keeps going round. We keep being given more and more transistors. So what do we do next? Okay, four microprocessors. 2006 version, 65 nanometers. The fire paths are there, and there's more memory, and there's very little else than memory and fire paths on something like this. So can we keep doing this? What happens if somebody gives me more and more transistors to spend on a microprocessor? Well, I run into a problem. Gene Amdahl observed, and this really is a law, it's got equations behind it and everything. If you've got a single problem to do, the speed up of multiple processors is limited by the sequential part of the problem. Equation. Brush past the equation and look at the graph. So let's take something that we think of as trivially parallelizable. Ray tracing is a very good trivially parallelizable application. In that, the work for every beam of light that you do is separate. They have a common back-end model that you're trying to ray trace, and there's some synchronization. So there is a bit of serial control around it. There's about 5% of your workload. So what does it mean to say, we'll take this trivially parallelizable ray tracing application and run it on as many processors as we like? What happens to our performance? Well, at first it's great. We keep adding processors and our performance keeps going up. And then, oh, the performance stops going up anymore. So the equation basically says that the limit of performance gain is dominated, so 95% parallel. That 5% means that you can only get a 20x speed up, no matter how many processors you add, 65,000. You still don't get 20x speed up. And in fact, the parallel part is so horrid that it even takes you 2048 processors, not 20, to get to 20x speed up. That's essentially the top of this line up here. So that's pretty bad. But ray tracing's an unusual application. It really is, really parallel. What happens if we look at something a bit less parallel? What happens if we look at something that's, say, 3/4 parallel? What does Amdahl's law mean then? That's this purple line. Oh, gosh. Clonk. Wait a minute, that's 90% parallel. No, 3/4 is the red line. So 90% parallel, we're limited at 10x. 3/4 parallel, we're limited at 4x. 3/4 of your application can be parallelized and 1/4 can't. You can only go 4 times faster, ever. If you're only 50-50, you've got half your application serial and half parallel, you can only go twice as fast, no matter how many processors you apply. Well, that's pretty bad news, really. The industry settled down into what I call the Multicore Consensus. And the industry can and will continue to make pieces of silicon with more and more parallel computers on them. They'll sell you as many primary processors as they can sell you, as many graphics processors, graphics being one of these trivially parallelizable things, as many special purpose processors. And that's going to be a problem because it's just not going to go very much faster. Traditional scalar computation hasn't been increasing for a while. If you've got something that's entirely serial, it just hasn't been going any faster for quite a long time. Since about 2006, your serial task has gone roughly the same speed. Things have changed a lot. I mean, the transistors we're getting are much more power efficient, but they're not a great deal faster, and that's a problem. Worse is to come. Scalar programming languages, C, JavaScript, Ruby, whatever you like, anything that's built on a scalar paradigm is a very poor fit for parallel hardware. We've been working for donkey's years on automatic compilation models to convert scalar definitions of problems to parallel hardware, and it doesn't work. We can do it for certain problem domains, and they're very limited. We're trying to force people to accept things like OpenCL, things that are explicitly parallel to start with, because that makes it much easier to run them on the multi-core machines. So we need a big revolution in software even to make use of this. You might think that that was bad enough news, but there's worse to come. So transistors have been getting more and more power efficient, but we use so many more of them in a small space. So things are getting hot. How hot? Well, here's a graph showing the thermal density of microprocessors. It's drawn by Intel, so it contains Intel processors. You can see that things just carried on for a while. They were making things that were increasingly hot till they got to the heat of a hot plate, and beyond to Pentium 2, then Pentium 3, and then Pentium 4. Everybody who remembers the NetBurst microarchitecture will know that Pentium 4 was a hideous mistake for Intel, and they were now well below the line, but still heading towards as hot as a nuclear reactor with a rocket nozzle not that far away, really. Pentium 4 broke Intel. They couldn't do it. They had assumed that they could make processors run faster and faster and faster. And they had to stop, throw away the Pentium 4 microarchitecture entirely, and go back, in fact, to this processor and create a new version of it, because it was substantially more power efficient than those things were. And that new thing is what's underneath core processors. So these are Core 2 Duos, Core i7s, as we go right off. So there is a problem. We can't get rid of heat in any particular way. So as we approach the sort of 100 watt per square centimeter, it's just impractical. Getting rid of that amount of heat is too difficult. So that the power density constrains the designs that we make. But it also constrains the future in a very bad way. If we look into the future, power constrains it too. So we've got this for, we've got our Core i7s, and they're using too much power now as well. They use the most efficient microarchitecture. Intel has refined the microarchitecture again and again. It's refined the transistor model, and size reduction of transistors has made them more power efficient. We're putting multiple gates. Intel call them multi-gates. Other people call them FinFETs because fins stick up vertically in the design of the thing. It's no longer a flat world. These are all to make the transistors not faster, but more power efficient. But even so, we're using so many more transistors in such a small space that it's a problem. As we go forward, we won't be able to turn our silicon on. 8 nanometers, somewhere in 2024, over half the die will have to be dark. Now, we're sort of used to our phones not running their microprocessors flat out all the time. But this says, even if we give 125 watt power into the die and the cooling method to get the 125 watts of heat away from it, we still have to turn half the die off most of the time. Otherwise, it's going to melt. So power and this thing called dark silicon defines some of our futures in bad ways. There are obvious ways to react to this. Design your system so it's got a heterogeneous array of microprocessors. Put down special purpose microprocessors for every eventuality. Leave them turned off until you actually need them. So one of the ways that ARM deals with this is to have what it calls big-little architectures. So you put down very big cores that can run very, very fast, and then you just put in lots of little very power-efficient cores. Big cores get a lot of work done, but not fundamentally power efficient. Little cores, use them most of the time when you don't need the breakneck speed. That's just a reaction to this, and it will happen more and more as we go forward. More special purpose processors will get bundled in to make up for the fact that most of the time we're going to have to turn everything off. But it's worse than that. So we have some economic problems looming. Economics has begun to rear its head for a little while. When we hit about 40 nanometers, design engineers and design engineer managers started to complain really quite a lot at how expensive this game was. In 28 nanometers, it costs something like $6 to $10 million to make a mask set, about $50 million to design a chip. So this has got to be a very expensive game. We're pushing on. We've got advanced chips on 20 nanometer chips in my laptop. Samsung just brought out a 20 nanometer chip for mobile phones. Intel are just on the crux, as they have been for well over a year now, of bringing out 14 nanometer chips, a processor called Broadwell Y, which will be the Core M architecture machines. So we're able to push on. It's getting very hard, it's getting very expensive. And as we go down, something bad's happening. We get more transistors on the die, but they cost more. The die is becoming so expensive. To make 14 nanometer, Intel had to use not only a very expensive set of masks to make it, but many of the metal layers, they had to have another set of masks, what's called double patterning, to get things exposed properly on the 14 nanometer design using 193 nanometer light. They need to put down a mask and put down another mask on top of it in order to shine increasingly small holes and get rid of the diffraction effects. So that's called double patterning. And it just means more and more expensive mask sets. And with more and more expensive materials used to build the vertical FinFETs and all the different layers of stuff in a chip, the die themselves are going up in cost all the time. And now we're seeing that we can make smaller, better transistors, but they cost more. So we're going to begin to see people flattening out. Another thing happened to Intel in 14 nanometer, which was it took much longer. It took Intel 3 years to get from 22 nanometer to 14 nanometer. And if they aren't in volume production of it by the end of this year, it will have taken 3.5 years, because that does seem likely. So this is sort of the end of Moore's law. It's getting really expensive per transistor. For Intel, they make a world out of really expensive transistors. They've been able to make their 14 nanometer transistors a bit cheaper than their 20 nanometer transistors. In spite of the die itself costing much more, the transistors are a little bit cheaper. But Intel started from a historic highly expensive transistor point. For companies that make cheap transistors like TSMC or Global Foundries, that's not true. And we really are going to see, as we shrink from 28 to 20 to 16 or 14, transistors are going to cost more. That's going to change the world in some really catastrophic ways. No longer will companies be able to bring out a design expecting to shrink it and make their money back in the future. Many companies aren't going to be able to come down here anyway. It's really expensive. So that's sort of where I ought to be closing for questions and things, but I've got 2 more slides. Oops. Predictions are hard to make, especially about the future. In April 2002, the head of Intel predicted 30 gigahertz, 10 billion transistor chips by 2010. We've seen some of the reasons that didn't happen. This is the graph they stood up with. In 2002, it got to there. And they knew that Pentium 4 was coming out, so they just predicted straight up there. And obviously, that was immediately before it went like that. So it's hard to make these predictions. I don't claim to be particularly precise about them, but I'm trying to give you some sort of idea of the character of what's going to come, which is this thing. A future of heterogeneous microprocessors and graphics processors means lots of work for processors and system-on-chip designers. That's me. And even more work for software people, because they need to catch up badly. And even so, we've seen massive gains in performance over the years. Though that's just not going to be repeated. If you're buying computers today, expecting them to be n times faster than they used to be, it's not going to happen. Might be more portable, might use less power, might have longer battery life. You know, I can have a really powerful laptop with an octal-core processor in it, runs off batteries long enough for this sort of presentation, but it's no faster than the 2006 machine was. And it might be that advanced chips start to cost more. Imagine all the industries that's going to disrupt when we say the next generation of your product, the chips that you want to go into that are better than the previous ones, are going to cost you more, not less than you're used to. So that's the end of things. Why didn't you go forward a slide, machine? So this is actually a processor at work. So this is an ARM. We've zoomed down on the outside package. We've taken the package top off and running a microscope grill across it. And this is ARM executing instructions. So as things flash, logical ones went down that path. And you can see the whole processor is being fed instructions, which is running an instruction simulator, and then being put over this animated layout. As you can see, lots of things happen all the time. It's executing instruction by instruction, but lots of things are going on all the time. We just zoomed into the register file, so we can see this is 1 bit in a register file. You can see lines being read and written. This thing is the barrel shifter in an ARM. It's responsible for shifting things. These are the instruction decoders. They're PLAs, just like the 6502s, and they're substantially simpler. So you can see as a green line across lights up, it decoded an instruction. And then we're looking at the priority encoder that does load multiple, store multiple instructions. That's the bit along the top. And then as we come to the edge of the chip, you can see instructions being fed down from the instruction decoder area and the priority encoder. It'll do it again. Right, I only overran a little bit. There's time for some questions.